Alright, we're going to be looking at Chapter 10. This is the chapter on lipids. And we're going to start on table 10-3. This is on the very last page of the chapter. So this is going to be on page 366. And I recommend you get a piece of paper out or just get your book out and take notes in your book next to the figures. And pause the video frequently when needed. And so to kind of organize this chapter, we're going to look at these different categories of lipids, and we're going to break them down into number 1, the category. Number 2, we're going to learn the general structure of each category, and then we're going to learn some specific names of each category of lipid. And we see the specific names given over here. And so the first is the fatty acid, and so we'll start on that. And so here is a fatty acid. The general structure of a fatty acid is a carboxylic acid right here with a long hydrocarbon chain coming off of the carboxylic acid. And we're going to focus on naming right now, how to name a fatty acid. And you'll see that you can break it down into 2 types. There's the omega fatty acids, and then the fatty acids that are not omega fatty acids. You'll see this delta symbol with a number hovering above it, and that tells you where the first double bond is. If a fatty acid is not an omega fatty acid, then you begin numbering it from the carboxylic acid carbon. And so if you want to know where the double bond is, you will count 9 carbons from the carboxylic acid. And this 18 in semicolon 1 means there's 18 carbons and 1 double bond. Now you have to be careful if you're working with an omega fatty acid, because you count from the opposite end with an omega fatty acid. And so if it is an omega fatty acid, like say it's an omega 3 fatty acid, then you start at this terminal end and you count 1, 2, 3, and that's where your first bond will be. And then up here, these are numbered normally. So these are numbered from the carboxylic acid position. So here this is a table detailing some information about fatty acids. So we'll notice over here we have the carbon skeleton. So we're going to increase by 2. So 12, 14, 16, 18, 20. And the names that we're going to be concerned about are the common names. And so remember, we're learning number 1 is category, number 2 is structure, and number 3 are some specific names. And so these are the specific names that you're going to want to know. So you have lauric acid, myristic acid, palmitic, stearic, and arachidic acid. And I have a mnemonic to remember these. Might not be helpful for you, but maybe it will. It's kind of ridiculous, but that's usually what helps you to remember a mnemonic. So you have Lori, and she's driving her car with my wrist. So just imagine somebody driving a car with their wrist. It's kind of ridiculous. She decides to switch to her palms. She begins to steer her car, and a giant spider drops down and frightens her. Okay, now we're going to look at the trend on melting points. So if you look here, you'll notice that the melting point is increasing. And we see a general trend that melting point will increase as we increase the carbon number. And that's because as we increase the carbon number, we're increasing the number of van der Waals interactions and hydrophobic interactions. And so as you increase the number of weak bonds, it becomes harder to boil, it becomes harder to melt. or break those bonds. And then also, if you come down here and you look at this semicolon, that denotes the number of double bonds. So you'll see 1, 2, 3, 4, and you'll notice that the melting point decreases. So we'll see the trend that melting point decreases as we increase double bonds. So this is just another slide of the fatty acids. This is showing a saturated fatty acid, which means every carbon has 2 hydrogens coming off of it, and there's no double bonds. Unsaturated means that there are double bonds in the structure, and you can have monounsaturated, which is what this would be, 1 double bond, or you could have polyunsaturated, which would be 2 or more. Here we're looking at more fatty acids, and this again is saturated, and this is unsaturated, and so we see that there are some double bonds in here. If you have saturated fatty acids, your plasma membrane is going to be, well, if you have saturated fatty acids, it's going to result in a less fluid or more dense state. If you have unsaturated fatty acids, they will kink, and that will result in a more fluid state. Our second category are Glycerol Lipids. And so it's important to understand the structure of glycerol. And so I drew a V here as an easy way to remember how to draw glycerol. Just imagine that you draw a V, and these are carbons right here. There's a CH3, a CH3, CH2, and then just simply draw an OH coming off of each carbon. So one OH coming off right here, another OH coming off right here, and another OH coming off right here. So if you look up here, it's a V with an OH coming off of each carbon. And so a glycerol lipid is a glycerol molecule with a fatty acid attached at this OH position. And so if you look right here, this is the OH with the fatty acid attached. And so these are joined via an esterification reaction. And the specific names of the glycerol lipids would be diacylglycerol and triacylglycerol. And so as you see here, this is a triacylglycerol because it has 3 fatty acids attached to it. This is a wax. It's a type of lipid. You have a fatty acid plus a long chain alcohol. And so you would have an OH here. Okay, so this would be the long chain alcohol. Go ahead and look at question 13. Number 3 are glycerophospholipids. So you'll notice the name is very similar to category 2, except you have this phospho thrown in here. And so we see here is our glycerol backbone, and we have fatty acids attached. However, we're going to have a phosphate group right here, and then we're going to have this X, which is a polar head group. And so let's imagine that we put a hydrogen here, okay, the wimpiest group that you can add on. If you ever add the wimpiest group on, you call that the parent molecule, and you give it a specific name, and that is phosphatidic acid. So if this were replaced with an H, it would be a phosphatidic acid. And then you just name the glycerophospholipid based on the polar head group that's attached. And so you keep this phosphatidyl, right here, phosphatidyl, and then you just add on the name of the polar head group. So phosphatidyl, 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 etc. And notice the word fat right there. You look at the word and it's kind of intimidating, but to make it a little bit more manageable, just remember that it says fat right in the middle. So if you eat a lot of lipids, you'll get fat. And also note that these do have a charge associated with them. Okay, the fourth group are Sphingolipids. This is the structure of a sphingolipid. Note that the backbone is not glycerol. The backbone is called sphingosine. So this is a sphingosine backbone. It's it's pretty similar to glycerol. You have the 3 carbons, so this would represent the V. And you would have an OH coming off of this carbon, an OH coming off of this carbon. But this is really important right here, that this is not an OH, it's a nitrogen group. And then also note that the sphingosine has a fatty acid-like chain that comes off right here with a double bond here. So the main differences between sphingosine and glycerol are the nitrogen and the fatty acid-like double bonded hydrocarbon. And so if you were to attach the wimpiest group onto here, the hydrogen, it would be the parent molecule, and it would be called a ceramide. And some more specific names are sphingomyelin. And you have gangliosides. These are kind of unique because you're not attaching a polar head group, but you're attaching sugar molecules. And these are what you know as red blood cells. So this determines the blood type on red blood cells. So this would confer like type O or type A. And so here we see a picture of some gangliosides. Here's the sphingosine backbone, and then there's the sugars. And so we see here this is type O, this is A, this is B. Okay, now we're going to talk about phospholipase. This is an enzyme that will cleave fatty acids, and there are 4 types. There's A1, A2, C, and D. And these are named based upon where they will cut the fatty acid. So A1 will cut the first fatty acid. A2, that 2 means it cuts the second fatty acid. Phospholipase C will cut before the phosphate, and phospholipase D will cut after the phosphate. So if you were to cut with phospholipase C, you would lose the polar head group, and you would lose the phosphate. If you were to cut with phospholipase D, you would just lose that head group. The 5th type of lipids are sterile lipids, and this is a cholesterol molecule. That's the parent. And the general structure is a 4 fused ring structure with 2 unique characteristics. Number 1 is the polar head, or the OH group, and number 2 is the alkyl side chain. And for specific names, you're going to have testosterone, you're going to have things like estradiol. It's probably not important to remember the names and structures of these, but it is important to understand how you get from cholesterol to these molecules. And you'll note that they all kind of look like cholesterol. They have a 4 fused ring structure, they've got some sort of polar head group, and they've got these alkyl side chains. And so to get from cholesterol to any of your other steroids, you're just going to alter this alkyl side chain and the polar head group. So if you snip a little bit off the alkyl side chain, you'll make a new steroid hormone. These are a class of molecules called eicosanoids. These 3 right here, 1, 2, 3, and they're hormones, paracrine hormones. So let's look at this molecule right here. It's called arachidonate, or arachidonic acid. So if we were to go back to this table 10-1, and look down here, 20-4, we see arachidonic acid. So it's a type of fatty acid with 4 double bonds. And we see 4 double bonds here. So arachidonate is a precursor to the eicosanoids, prostaglandins, thromboxanes, and leukotrienes. So arachidonate would be in the plasma membrane, and you would use a phospholipase to cleave it, and then it would become the precursor to one of these molecules. Note that NSAIDs will inhibit prostaglandins and thromboxanes, but not leukotrienes. And NSAIDs are also known as aspirins and ibuprofen. But it's important to know that the NSAIDs will only inhibit prostaglandins and thromboxanes. Alright, what was the next one? I think it was isoprene or prenols. Let's see. Okay, renal lipids. That's the next category. And so renal lipids are all composed of isoprene units, which is a 5-carbon unit that repeats itself. And so here we see 1, 2, 3, 4, 5, a 5-carbon unit that is repeating itself. So we see that repeating itself. There's 5 types that we see here. Well, looks like more than 5. There's 6. So you have vitamin E, also known as a tocopherol. You have vitamin K, important in blood clotting. And you have warfarin. This is found in rat poison, and it will cause you to bleed to death because it is a competitive inhibitor for vitamin K, which aids in blood clotting. You have ubiquinone, which is found in the electron transport chain. You have plastiquinone, which is found in photosynthesis, and then dolicol transports sugar precursors onto your proteins, which will then become glycoproteins. Here we have vitamin D. This is a fat-soluble vitamin, and this is a little mnemonic to remember all the fat-soluble vitamins, A, D, E, and K. Notice that the carbon 9 and 10 will be cut, and that will activate vitamin D3, and UV light is what will activate that cut. And notice it looks a lot like cholesterol. You have the polar head group, and the alkyl side chain has just been altered a little bit. This is vitamin A, very important in the vision pathway with retinol. Lipids can also serve as color pigments, and so they are what give this bird the red color and the yellow color. And that's the end of the presentation.